Thanks to Pierre for the invitation to come down here and tell you about the RAPID facility. So we are a NEARI facility, much like the Shake Table at San Diego, the Wave Tank at OSU. We are a equipment facility that people can write proposals to National Science Foundation and as well as for other funding agencies to actually use our equipment. So I'm going to tell you about the equipment and our team and some of the work we've done over our first quarter of operations. We became operational after a 2-year kind of build-up. We became operational in September 1st. So our team is, it's an interdisciplinary team. Joe Wortman is a geotechnical engineer. He's the PI and director. I am a structural engineer. I am kind of the operations director. Mike Olson from Oregon State University is a geomatics expert, and he is our technical implementation director. And then we have contributions from folks in coastal engineering, wind engineering, additional structural engineers, and also social sciences. So we are an interdisciplinary, kind of multi-hazard research facility, and we have kind of expertise to help people kind of use our equipment to do reconnaissance, kind of representing all of the hazards and all the different disciplines. So the vision for kind of our vision or mission for the RAPID facility is really to enable researchers who do field reconnaissance to collect an unprecedented amount of high quality data that ultimately can be used to address grand challenges in natural hazards engineering. And so we want to develop the tools, the protocols, and have the staff expertise that can really kind of help push reconnaissance data collection kind of into the next generation, and really also expand the community of investigators, of those who perform reconnaissance. It's largely been a pretty closed community. We want to open that up and make these tools available to kind of the next generation of researchers who can make their own contributions from the real world laboratory. So that's kind of where we see the RAPID fitting in terms of the overall addressing kind of grand challenges in natural hazards engineering. So the RAPID facility itself, what we do to kind of enable that mission is, or to achieve that mission is we have these kind of 6 we call strategic activities. We've acquired and then we maintain and operate a portfolio of state-of-the-art equipment. We develop and support a mobile application that assists reconnaissance teams in the field. We provide advisory services. We facilitate the systematic data archiving of the collected data. And we train, we've got user training on how to actually use our equipment in the field. And then we engage the public as well. So the notion of transforming natural hazards reconnaissance, what we're really talking about is, for decades, we've used observations from the real world to make very important advances in our understanding of how natural hazards impact civil structures, infrastructure, and these things. And a lot of really important advances have been made over time. This is a slide from John Bray, illustrating, field data collection. This is a building that had settlement due to liquefaction, and they're making very important measurements to understand how liquefaction affected this building, what may have triggered the liquefaction under this building. A lot of advances have been made in this from these types of observations, but these are 2D observations at maybe 10 centimeter at best resolution. You're not getting a full picture of what really happened to this structure. And so the vision for our facility and our tools is to allow reconnaissance to kind of inform a more complete understanding of what's happening in the real world. And so what we have are a suite of tools to collect 3-dimensional, high resolution, high accuracy data. One example is laser scanners, and I'll walk you through our portfolio of laser scanners. But with a LiDAR scanner, you can actually get a 3D point cloud at, we're talking about millimeter resolution, and you're getting the full 3D displacement field and a much better description of what happened. We can also automate this process, the data collection process. We can ensure that it is standard and uniform across those who perform reconnaissance, so that when we go back and look at this data in 20 years, we understand the methodologies that were used to collect it, and there's a uniformity among, and a reliability then that comes with the data. So efficient data collection, we can automate the process a little bit, and then obviously we can share this data, via the NERI cyber infrastructure, design safe down the road, and it can be available for everyone to learn from. And then later on, with this collected data, with this really nice 3D data, you can continue reconnaissance back in your office, right? That's through continue interrogating the data, learning from the data with virtual environments, or just even in 2D, you can learn a lot from this data as well. So that's kind of our first vision of how the Rapid Facility is going to, or we're working to transform natural hazards reconnaissance. The other one is in collecting, kind of bridging the gap between what has been largely kind of interviews, the way social science data is collected, the way people experience natural hazards, and how that often is disconnected from the physical realities of and the damage of the infrastructure that they experienced. So we often have a really hard time connecting that social science data and the physical data that's collected in the field. And so we're working to kind of bridge that gap and develop software and platforms that actually allow us to connect social science data that's been collected from reconnaissance with some of the detailed engineering data. So just an example, damage from tsunami inundation, we have like a high resolution laser scan. We know where that is. It's geospatially located, so we understand where it is in the context of damage. Now we go and do interviews with our software. That software is geolocated, so we understand where this person is. We can put all this information together through our app, and then feed it to design safe and essentially integrate that social science as a GIS layer for future investigations, and really try to connect kind of through the disciplines our observations of what happened in a natural disaster. So that's just a brief overview of what we do, of kind of our vision for what the facility can and will be. So we're an equipment site, just like a shake table. So I'll walk you through a little bit of the equipment that is available for really anyone to use. So we have a series of advanced geomatics technologies. We have seismic instrumentation. We have wind and storm surge instrumentation. We have social science reconnaissance equipment. We have ground investigation equipment, a whole host of different imaging equipment, and then software tools, and some high-speed custom computers to help with data processing at our headquarters at the University of Washington. Just to show some pictures of some of our more interesting pieces of equipment, we have a fleet of drones ranging from kind of hobbyist level to really nice advanced UAS systems. Our kind of premier piece is this Mini Ranger system, which is a LiDAR equipped, laser scanner equipped UAV, and really nice. So we have a full different, anything you would want to do with a UAV for data collection, we can do. We have a suite of laser scanners ranging from small range laser scanners. The BLK360 has about a 60-meter range. It is excellent for doing building assessment. So you can do a scan in about 6 minutes with the BLK360. It's high resolution. It gets a full 3D field, and so you can move room to room to room in a building very quickly. Then we have two longer range scanners that are great for exteriors. They're also great for landslides and liquefaction over kind of broader areas. All of the equipment that we've bought is a focus on portability, ease of kind of getting it to the field, and ease of our users actually using the equipment in the field. So an eye toward portability as well as kind of durability. The long-range scanners that we use are from MapTech. They're a heavy-duty laser scanner that's been used a lot in the mining industry. So they're very robust. We have surveying technologies as well, so total station and GPS receivers, and so all of this works really together with the laser scanning and imaging equipment. And what we're doing is when we collect the laser scanner point clouds, we're using the surveying data to improve the accuracy and resolution of those point clouds. So the more points that we can geolocate to a high precision with our surveying equipment that appear in the laser scans, the better accuracy we can get with the laser scans. And so all of this equipment works together, and we can help train people on how to actually do this in the field. We have an applied Street View camera. This is kind of a, Google Street View costs like a couple $1 million. This is a kind of baseline version of that. It's an 8-camera system that you can mount on a car and actually drive through neighborhoods following natural disasters and produce. We've got the software to actually produce a Street View environment from the collected data. We have a host of different imaging equipment, from ultra high resolution cameras, thermal cameras, Gigapan, which kind of works with the high resolution cameras to put together really nice panoramics. It's very, very good for doing landslide evaluation from afar, and 360-degree cameras. We have backpacks all ready to go with kind of the more conventional hand tools and safety tools that you might need for reconnaissance, and happy to ship those out for those who don't have them. We have coastal equipment. We have an unmanned automated boat with a single beam sonar to do bathymetry mapping, useful for tsunamis and for storm surge before and after events. And then we have our Reconnaissance App, which is really our key piece of social science data collection equipment. It has, we're working with a social scientist to put together surveys that are already, past IRB protocols and all this stuff. So all of that information will be built in. So you can do surveys, you can do interviews, you can photos, all kinds of different things. And the software also helps with mission planning and data collection and coordination in the field. We use it to collect metadata associated with the data we collect with our instruments. So you know where you were and what the settings were on the LiDAR scanner for this scan, and all of that gets put together and put up to design safe in a very automated fashion. And so we're working to tie all that stuff together. And then we have a data processing facility at our headquarters at the UW, and we also have a 3D visualization cave. So if you've done field work and you don't have a way to interact with the three-dimensional data, often the software in 2D is fine for doing evaluation. But if you want to interact with the data in a three-dimensional way, you can come and sit for a week in our and work in our cave environment to interrogate the 3D data. To use the Rapid, we're really open to anyone. If you're a researcher at an academic university, you write a National Science Foundation grant to use our facility just like you would for any of the other NERI facilities. But we serve all different institutions. We've done work already for ODOT and other agencies. So our major funding's from NSF, but just like all the other NERI facilities, we're open to performing work for really anyone at FV, of course. Yeah, thank you. So we have done, so we became operational on September 1st, and within the first 3 months of operation, our first quarter of operation, we had 150% of our expected deployments for the year. Because on right after September 1st, we had an earthquake in Hokkaido, Japan. We had Hurricane Florence, Hurricane Michael, the Indonesian earthquake and tsunami. And then we've been working at a landslide at Oregon State as well. And then we are also actually sending laser scanning equipment over to eDefense for a shake table test that's going on there to scan these wood frame houses before and after and look at damage. So we've had a ton of work over the first 3 months, and I'll just highlight a little bit of the data that's been collected. Largely we're working with teams of researchers. We provide the tools and the expertise to use the tools. They bring the research questions, okay? And so this was work that we did with GEAR, a GEAR mission to Hurricane Florence. And this location, let me see if I can bring up the pointer really quick here. Here it is. So here, you can barely see it here. This is actually an earth dam, and there's a spillway here that allows water to move into this river that then gets covered up by the trees, so you can't really see it. This dam actually failed during Hurricane Florence, and we were able to fly it, get there with the GEAR team and fly it with one of our UAVs and develop some really nice structure from motion models. So let me see if I can get this to play. There we go. So here's a fly-through of from a 3D point cloud that's been developed using the aerial photographs from our UAV. It's a structure from motion model. That's the technique that's used. Really, there's great software to do this. We didn't do much cleaning. We had to do some cleaning. But you get a good idea of kind of the level of damage, for this particular dam failure. The idea, of course, with these 3D data sets is we're able to make measurements, and so and continue reconnaissance back in our offices. So here's an example of being able to take measurements. So in this case, we're measuring the diameter or the length of the width of the roadway at the top of the dam. But we can use that also to make volume measurements. We have an estimate now of the volume of the dam that was washed away, and stuff. So really, advanced kind of data collection and really transforming our ability to do reconnaissance and what we can learn from these reconnaissance. So here's an example data set that was collected by a GEAR team in Hokkaido, Japan. And I have to export these as a PNG and then put them in PowerPoint. When you open these point clouds up in the software, they look a little nicer than they do here on the screens. So this is a collection of about 8 long-range laser scans from this neighborhood in Hokkaido that had liquefaction-induced settlement over a large area. And so you're able to map out the extent of liquefaction, the 3D kind of topography of the settlement, and then you're able also to zoom in and make some very specific measurements on deformations and settlements of specific structures. So again, an example of what you can do with these point cloud models, point cloud data. This is a laser scan. It didn't come out. It looks so much better on my screen than it does up here. I apologize. But this is a point cloud data that was collected with a rapid grant from NSF to look at large volume buildings that had a high rate of failure in Hurricane Michael. And this is the windward face of a marine storage building. So these are big, open, kind of warehousey buildings. And the windward face is collapsed here. It's the same failure mode kind of over and over and over again with about a dozen different buildings that we visited after Hurricane Michael. So to collect this point cloud, we did about 20 laser scans in different places, both with a long-range scanner inside and then our short-range scanner. To get detailed work on the, I'm almost done, up close in the damaged area. And so this gives you an idea of the point cloud looking at the damage, and we're actually able to make nice measurements. We have measurements of the heights, we have measurements of the depths of structural elements, And I know, again, these don't project all that well, but we can actually get, with the scanning that we did here, we have a really good measurement of flange thickness and web thickness on all the structural elements. And we verified those with caliper measurements when we visited this building. So it gives you an idea of what you can do. And then just an illustration of data collected with the Street View camera. It's, again, that 3D Street View environment that we're all used to seeing. And then, of course, you can take all of this fancy equipment and complement traditional experimental instrumentation that we've used for years in large-scale testing. And so here's a shake table test that was conducted at UCSD on a wood frame structure, and we have some really nice point cloud data where we can actually identify cracks in the cross-laminated timber from laser scans of this particular test specimen. So that's kind of a brief introduction to the Rapid facility and its capabilities, and we look forward to working with all of you and your excellent research ideas, and really I just want to get everyone thinking about how you might use these tools in the future. So with that, I think we're about 10 minutes late for the break. I don't think I caused all of that, though. So.